Recording is rolling. So welcome to Wednesday, January 12th. Yesterday I did some notes and some demos with you guys, and today is going to be kind of like yesterday. We'll just do a few more notes, a few more demos, fill you guys in on anything related to waves and sound. So here's our agenda. Let's start with some posters here. There have been some new posters hanging from my ceiling last few days. And gone over some of this material. So this is, I think, a good recap of some stuff you guys seen last couple of days. Right, so we're doing harmonic motion and also waves. There's a lot of crossover, so I just teach this all at once. Right. So this nice looking classic transverse wave has some properties. Has an amplitude, has a wavelength, crest to crest, or this node to this node, some fundamental wavelength. Right. If you're watching these, let's say ocean waves come in, like go bob, 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 there's some associated frequency, which is the reciprocal of the time period. And if you know the frequency and you know this wavelength, then multiply those together, you get the wave speed. We've got time period of a pendulum. This was the lab you guys just did. You guys figure out for this harmonic motion, how much time to swing back and forth. Really good proportional type question you can get from this is something like this. What if you had a pendulum that was 4 times the length, made this 4 times as long? What would happen to the time period if you throw 4 in here? What's the square root of 4? 2. Ooh, so 4 times the length. You actually have twice the time period to swing back and forth. Right? You know what the formula is really similar to? I played you guys an animation of a mouse bobbing up and down on a spring. Right? Guess it has like the same structure formula. Right? So what's the time period associated with 1 full cycle for this guy? Well, looks pretty similar, except it's 2 pi square root m1k. I showed you guys an animation of some standing waves yesterday. Now for a string, there's certain standing waves you can set up, got half a wavelength, 1 wavelength, 1.5, 2. So there's like a certain pattern. Remember, standing waves, you can touch it at this node and it doesn't affect motion because that point doesn't move. Now the next lab we do, which is probably gonna be next week, we're gonna set up some standing sound waves. Now sound waves are longitudinal, not transverse, but there's a whole story of that, so say that for the future. But say you have like a pipe that's closed at one end, open at one end, maybe like blowing into a glass bottle. Actually, it's going to be pretty similar to an upcoming lab. Right? You can set up standing waves also, but works out a little bit differently. There's 1/4 of a wavelength, 3/4, 5/4, 7/4. So look for that in the future. I just want to introduce that idea to you guys now. So there's a pattern there. It's just a little bit different than it was for the strings. And then if it's open at both ends, like a flute or like a lot of wind instruments, well, there's some patterns too, but they work out a little bit differently. Right? So same pattern of those. Right. Yesterday, I think I got to about the Tacoma Narrows Bridge. So let me go back and share my screen and pick up from that point. Tacoma Narrows. Here it is. So this bridge was built back in 1940. This thing opened, it bobbed up and down a bit, but engineers kept an eye on it until one day it goes into this torsional type shape, right? It has this like twisting motion. There's a time period there of about 5 seconds, if you count it out, about 5 seconds. How many hertz, what frequency is that? 1/5. Yeah, like 0.2 hertz. Right, so 5 seconds time period, 0.2 hertz. Hey, that might be the resonant frequency of that particular bridge. This is why you don't have troops marching over a bridge, because if you hit some multiple of a resonant frequency, something like this might happen. So after a while, a few hours, there was an engineer walking out there. He was able to get off this bridge before this happens. This whole thing collapses. So what was wrong? What was the engineering flaw? And how did engineers go back and design a better design to fix this bridge? Well, there's a hint sort of in this snapshot right here. We can see what went wrong. It has to do with how they designed the structure of this road right here. You can kind of make it out. Do you guys see like a vertical girder type pattern going on there? Right, so let me flip back over and show you story is behind that bridge, what engineers learned from that bridge. So they were thinking when they designed this thing, well, there's going to be a lot of cars that are driving over the top. And these cars, well, that's a lot of vertical weight. And if you orient materials like vertically, say like have a vertical girder structure like you just saw in that snapshot, something like this, then that should be maybe like the best at handling vertical loads. And actually on the face of it, on paper, that's not necessarily a bad idea. Let me show you guys why. I've got this accordion type paper. And I have this 100-gram lab mass, which weighs about 1 Newton. It's like 0.98 newtons. So let's call this 1 Newton of weight. Now, can this support this? Well, let me do this first. I'm going to smash these together. Great. Bunch of tall, skinny triangles. See a bunch of tall, skinny triangles? Let's check this out. Do this upside. Okay, so looks like it's gonna work. Oh, there it goes. Okay, so yep, that can support that. That's able to hold that right there. It's able to support it, hold it up. Okay. What if I do this though? What if I spread this out? Get a bunch of flat Y triangles, Is this still gonna hold it? No, it's gonna smash right down. Okay, so tall triangles could hold it, but not the flat triangles. And what this is consistent with, a lab that you guys did a long time back. You guys remember the spring scale lab? You're doing different things with the spring scales. Now that was tension and this is compression, but it's same principle. Think about how the vector components work, do some trigonometry. So anything that's vertically oriented is better at handling vertical loads. But you know what this design is terrible at? Is anything to do with a horizontal force, which this Tacoma Narrows Bridge, it's over in Narrows, there was a bunch of crosswind sweeping straight through. There's a horizontal force right there. Okay? And that's where this thing went awry. So go back and redesign this thing and rebuild this thing, but they made one small change and it made all the difference, and the bridge was perfectly fine after they rebuilt it. So instead of a vertical girder system, you want what kind of system? Triangles, yeah, like a truss system, a triangular truss system. Do something like this. Okay, so now that can handle vertical, but also can handle any kind of horizontal force too. So what's that story? All right, let's look at, let's talk about earthquakes. So let me switch my screen over. There. Let's go back just over 10 years ago. There was one of the largest earthquakes ever recorded off the coast of Japan. This was a magnitude 9 quake that's about to hit. You guys are seeing security footage of a pole as this thing's about to hit. Magnitude 9 quake, by the way. You guys know the Richter scale? If you have a magnitude 8 quake and then a magnitude 9 quake, a 9 is 10 times more powerful than an 8, right? Because it's a logarithmic scale. Hold on to that idea. I'm going to talk about that more later. But okay, so we're watching, all right, this pool, right? Find it. You guys want to be swimming in that pool? Looks fine, right? Ooh, ground starting to shake. Right? Not too bad though, right? It's just shaking a little bit. Right? The pool water still looks fine. You'll be in there, right? I think, right? What's this? Oh boy, now we're getting okay. It turns out that whenever you have an earthquake, there's actually 2 different kinds of waves that are sent out: P waves and S waves. Right? Hey, that's what is? This might look familiar because yesterday I played a very similar animation. You guys remember this animation from yesterday? Longitudinal waves versus transverse waves? That's what P and S are, right? So P waves could be like pressure waves and S waves could be shear waves, right? Pressure versus shear, right? Because there's longitudinal wave is literally a pressure wave, right? And then that shear motion on the top one, that transverse wave, that's what's going on there. It's something like shear motion. But you know what else I've heard the P and S also stand for is primary and secondary. Like I've heard both, like pressure and shear, but also primary and secondary. And that's also accurate because these waves travel at different speeds. And P waves actually travel faster. So if you're in an earthquake prone zone and you feel the earth start to shake like an earthquake's coming on, it's usually those P waves that are hitting you first, and you get a good warning before those S waves hit. You guys just saw in that video footage, those S waves do a lot more damage. And so get a few seconds of warning to like get them, say, under a table or outside the building if you can get outside in time, like that. Let me flip back over and show you guys how you can actually take advantage of that to figure out the epicenter of an earthquake. So, side note here, if you just I mentioned like that was a magnitude 9 quake. Right? If you're talking about a magnitude 7 quake versus magnitude 8 quake versus magnitude 9 quake, right? It's really 10 to the power 7, 10 to the power 8, 10 to the power 9. When you say a magnitude 9 quake, you're really reading the exponent. So that Where'd my calculator go? This at the end of class today, you guys are going to see some logarithms. So I want to remind you guys that what if I did like log base 10 of this number, 10 to the power 7? That spits me out this number on the calculator, 7. Okay, so if you take a log, it's really telling you what the exponent is, right? It's telling you the power. So when you say magnitude 7, wait, you're getting the exponent. What is log base 10 of 10 to the 8? 8. What is log base 10 of 10 to the 9? 9, which is the quake that you guys just saw in that footage. Now, how can you figure out where the epicenter of a quake is going to be? Well, all over the world are these seismograph stations that have these rolls of paper that are rolling, let's say right to left, just all day, every day. And because nobody knows when the next big quake is going to hit, where it's going to hit, like what its magnitude is going to be. Earthquakes are notoriously difficult to predict. But there's this ink pen that's attached to a big old mass that's attached to like some spring, maybe attached to the outside world. Right? And all day, every day, paper scrolls by and just leaves like a straight ink line. Right? So real boring. This might go on for years. We just get like straight lines just for years of this going on, right? Until finally the big quake hits. And when the big quake hits, what changes? Well, the entire ground is shaking, right? But take a look at this ink pen. The fact that you attach it to a huge mass means there's a lot of inertia. Ooh, a lot of inertia. Didn't want to move. And also the fact that it's attached to a spring, it's really hard for the earthquake energy to propagate along the spring. Right? Okay, so the pen is isolated. Meanwhile, the rest of the world is shaking around it. And then if you unroll this paper and take a look at it after the fact, you're going to get a reading that looks like this. So maybe for years it's just been a flat, boring line, and then all of a sudden you get and then after a while this you get just like you guys saw in that video footage, and then back to that, right? Okay. So and you can see what kinds of waves are going on here. Here's your P waves right here. That's P. And then here's your S waves right here. S, like that. Okay. And the fact that these waves travel at different speeds, if you know what those speeds are for your particular region, now it's different depending on where you are on Earth. You know, the crust is different, there are different kinds of rocks. Right? But if you can figure out what those numbers are, you can figure out how far away the earthquake happened. And I'll show you guys why. Let's suppose, for example, that you were right on top of the epicenter. So you've got this whole station just sitting right on top of a fault line. And then the fault slips and like bam, the waves just hit you all at once. You wouldn't even have a P wave warning. Like they would all just hit you at the same time. It would just go from a flat line straight to S, wouldn't it? Just like bam, just like happy birthday, no warning, just earthquake day. Hey, maybe the longer the P wave warning, maybe that's like an indication that the earthquake happened further away, right? The epicenter. Right? In fact, if you know the difference in speeds between the P and the S, one of your textbook problems does this too. I forget, I think I assigned it as a bonus problem, I think. Right? I forget for sure. If you know the difference in speeds and you look right on this paper, you can determine the time of that warning, that P wave warning, time, speed times time. Well, that would tell you some kind of distance, wouldn't it? Because distance is equal to speed times time. And then that's how you can figure out how far away the epicenter happened. Well, kind of a catch though. You don't know in what direction. You just know, say it was like 100 kilometers away. Okay, so if it's like 50 kilometers an hour for 50 kilometers a second for 2 seconds, it's 100 kilometers away, something like that. Okay, so then let's get satellite point of view, aerial point of view, and we're looking at all these stations, like all over the map. To say these stations are hundreds of kilometers away from each other. Okay. Let's say we're at this one, and maybe this one's the station we were just looking at. We've got, okay, so something to do with like 100 kilometers away. So I'm going to make a circle, radius 100 kilometers around that station. The earthquake epicenter happened somewhere on that circle. Then we start calling up these other stations, like, hey, you guys, where's the earthquake relative to you? You say, well, it was also 100 kilometers away from us. Like, oh, okay, so like same size circle. So 100 kilometers away from this station. Okay. Then we call this guy up over here, say and say how far. This guy's like, oh, it was a long way away. It was like 400 kilometers away. Like 400 kilometers. Whew, we need like a huge circle that's gonna like go off this paper. It's like something like this, right? And what you'll see is that they all kind of converge on a single point. Maybe we'll call it the force station. Call it this guy right here. And this guy's like, ooh, it was really close. It's like 50 kilometers away. Ooh, 50 kilometers. It's a tiny circle around you. Right? But they'll all meet at this epicenter. Right? And that's how that is determined. Right? I got some Paul Hewitt demos for you guys. So switch back over.
Hi gang, sound time. If this room were filled with ping pong balls and I had a big paddle and I shook it back and forth, I'd send vibrations through this ping pong balls. Same type thing happens when I strike this tuning fork. This vibrates back and forth and hits the air. And the air vibrations, that's what you pick up as sound. You ever have a fork of frequency, same. Watch, listen to me. Strike this one vibrates. Or, as long as the frequencies are matched, I can get the vibrations to cascade back. It's called resonance. Huh? What happens if this fork has a different frequency? Let's try now. Yuck, nothing. I have to have this frequency the same as this to pick up the vibrations from here. That's what happens with a radio set. Your radio signals are coming in and you change the frequency of your radio set so that it matches the incoming frequency. You got it. Physics. Yay.
Right, but what if the two tuning forks were slightly different and you hit them both at the same time?
Let me get these things so they're a little bit different in frequency and strike them both at the same time. Can you hear the throbbing? That is a result of. Can you hear the throbbing? That is a result of interference, and the phenomenon is called beats. All right.
It's a wow, 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 wow. Let's say that that's approximately 2 hertz. That sounds pretty close, right? About 2 hertz, about 2 beats per second. Wow, 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 wow. So the frequencies that you would need on those tuning forks to make that happen would be 2 hertz away from each other. This is how it plays out. So for example, I don't know exactly what they are, but let's say, for example, it might be like 400 hertz and 402, or maybe it's like 350 and 352, but it's like they'd be 2 hertz away from each other. And then that's how the beat frequency would be 2 hertz. All you do is just subtract the two from each other. Okay. I do have one more Paul Hewitt for you guys today, but I'm gonna hold you guys in suspense because I got a live demo first. Okay, so I have here a piezo, a 9-volt battery, and a bunch of yarn for padding. I just put this together. So you guys hear that tone? Okay. So there's some frequency associated with that. We stuff this down into this yarn. And just swing this around my head. To tell you what, if you're watching the video, just so you know what's going on, it goes so fast. Okay, what I'm going to do is take this piezo and swing it around in a circle. Okay. You guys tell me what you hear from this. Okay. Do you guys hear a pitch shift, pitch change? Is going up, down, up, down. Okay. Now I have to take you guys' word for it because I'm at the center of the circle. So I just hear one solid tone. Is it rising as it's going towards you and down as it's going away? Okay, so everybody in this room hears something a little bit different depending on where you're sitting. Let me try it over here. It's so here's this different. Right? What's that effect called? That is the Doppler effect. Yeah, Doppler effect. You probably run across this anytime you're standing out by the side of the road and hear a car go by. It's like, one thing I kind of wonder is, I wonder like 200 years ago if anybody ever experienced the Doppler effect. I mean, it's kind of a common thing today. I'm going to let Paul Hewitt explain this, and I'll go back and fill in some details.
When you're like a bird, you're looking right down in the water, and there's a bug sitting there. And this is a lake that's perfectly smooth.
But now what the bug starts to do is the bug starts to jiggle up and down. And when that bug jiggles up and down, that bug is a vibration, yeah? And that's vibrating on a nice surface, yeah? We're gonna make what? Begin with a W. All right, all right. We're gonna make waves, gang. We're gonna make waves, okay? And the waves kind of look like this. Draw the line that represents like the crest of a wave, like it might sort of be like this. You see what I'm saying? Okay, so this represents the crest of the waves. And the waves go out in all directions. And the fact that they're circles is kind of evidence that they go out in all directions at the same speed. Isn't that true? Like if it went faster over here, then the wave would sort of be like that, yeah? Okay, so the circles are evidence of the same speed. Okay, now what would be the frequency of the waves compared to the frequency of the vibrating bug? In other words, if you put your hand here, blip, 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 the waves would hit your hand, yeah? Certain frequency. How would that blip, blip, blip compared to the whoop, whoop, whoop of the bug? Same. Isn't that right? The frequency of a wave is the same as the frequency of the vibrating source. Makes sense, doesn't it? Let's suppose now that the bug swims in this direction. What the bug is going to do is the bug is going to swim in the direction of the waves that it's producing, and it continues to vibrate a little bit, yeah? Wouldn't the wave pattern look something like this? Can I be seeing that? In fact, what direction would the bugs be swimming, gang? I mean, you can tell it's going that way, right? Well, the bug might be at rest and the water's going this way. I mean, motion is relative anyway, yeah? Okay, now if I put my hand over here, would I get a higher speed wave, a lower speed wave, or the same speed wave? Check your neighbor. And make sure you're listening to the question that's being asked.
He gave you kind of a curveball type question. He said if you have your hand on the right side and those, let's say those represent wave crest, what happens to the wave speed compared, right? Now, once that ripple has been released into the water, isn't it just traveling at whatever speed it goes through in that particular medium, like in this case, the water? Does it care about the motion of the bug behind it anymore, like that particular ripple? So does the speed of the wave change depending on the speed of the bug? Maybe not the speed, but what physical quantity might actually be different? Not the speed, but the frequency. Yeah. Okay, you guys get this.
How many people say, hey, the speed of the wave is going to be the same? Yeah, that's right. The speed of the wave doesn't change. What does change, gang? How frequently that wave encounters you is different, yeah? So I can get a different frequency. When I put my hand here, higher frequency or lower? Can you see it? Over here. That change in frequency due to motion of the source or the receiver is what we call the, named after a person. Okay, good. It is called it's a Doppler effect. That's right. The Doppler effect is the change of frequency when something moves toward you, away from you, that sort of thing. The change of frequency due to motion.
All right. So we go back and I'm going to add to that story a bit. Right, so I'm going to have a line of travel. Instead of having a bug, I'm going to have like a jet. Right, so let's have a jet going. Right, traveling left to right. Maybe that jet has some jet engines, like sending out a sound like. And here's the sound waves from the jet. Well, it sounds some sound waves back here, and back here, and back here. I'm really just gonna copy paste that Paul Hewitt drawing that you guys saw. Set up. So circle, circle, circle. Okay. Doing something kind of like this. Okay. All right, so, okay, so I see that jet is sort of like catching up to the various sound waves it's sending out. It looks a lot like a Paul Hewitt picture. What if you are standing here and it's just, the jet is heading towards you? Wouldn't you hear a higher pitch? Like, okay, so that'd be a higher frequency, kind of like a higher musical note, versus if you're standing up here, you'd hear like a lower frequency, a lower musical note, sort of thing, right? Remember what these circles represent. It might represent wave crests. If I draw these really are sound waves, but if I represent them as longitudinal waves, they're like crest, 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 right? Versus crest, crest, crest. Sorry. I'm gonna make up some numbers and write a Doppler formula for you guys. We'll make an equation and then solve this, to figure out what these guys are actually hearing. Let's say that the speed of sound is really the speed of a pressure wave through some medium. So through the air at 1 atmosphere at room temperature, it's approximately 340 meters per second. So I'll use that for this example. Let's say that the speed of the jet is like 100 meters per second. And let's say that the frequency of the jet engines is, just make up a number, let's say like 300 hertz, just to pick up some numbers. Well, this guy, the jet is headed towards, he should perceive something that's higher than 300 hertz, right? Maybe 350 or 400 or something like that. Right? Let's solve it. And this guy is probably lower than 300, but we'll figure that out. So Doppler formula goes like this. The frequency observed is equal to the source frequency. Actually, that's the entire story as long as nobody's moving, right? If everybody's just at rest, then everybody agrees on what the frequency is, right? So you're in the plane, you hear it's on the runway, and everybody else talks, you hear But if you're in motion, you have to take that source frequency and multiply it by this ratio. It's going to be the speed of sound. It shows up here and here in the equation, so it shows up 2 places. I'm going to put this together piece by piece because I want you guys to think critically, see if you can think a step ahead as I'm writing each part. I'm going to put the speed of the source here, which is like the speed of the jet. Now, what's going to connect these two? I haven't finished this formula yet, but let's just think. How about this? I'll start writing in some numbers. I still have some more to add to this formula though. Like I know the source frequency was 300 hertz, so it's like 300 hertz multiplied by the goal fraction. Speed of sound, I'm using 340 meters per second. That goes there and there. Okay. The speed of the jet was 100 meters per second. Okay. Now I know that this guy right here is observing something that's a sound that's more than 300 hertz. Like if the jet's going, this guy perceives like, so that's maybe 400 hertz, maybe something like that. Okay. So how can I get a number that's more than 400 hertz? Or for that matter, if this guy perceives like really low pitch, how can I get some general formula so that I can get 2 different frequencies depending on your point of view and your frame of reference? Well, maybe I could get that by applying, hey, how about like a plus or minus sign? Wouldn't a plus or minus sign be able to handle 2 different situations? Okay. So that's what's going to go right here, plus or minus. Right? So like adding or subtracting. Okay. Let's just have these guys at rest, just for simplicity for now. Okay. Now the question is, for this guy right here, the plane's head towards, should I do plus or should I do minus? Okay. Can you guys figure that out? What operation would you need so that the observed frequency is greater than 300 hertz? Well, if you did plus, wouldn't that make the denominator really big? Wouldn't that make the overall fraction small? Right? So speed of sound over speed of sound is 1. So how do you pump this fraction up more than 1? Well, you need to decrease the denominator, right? It's going to be subtract. You see that? It's going to be subtract. Okay. So let's see what that would be. What is 300 times 340 over 340 minus 100? That is 425 hertz. Okay. That's the perceived frequency. That's what this guy hears. He perceives 425 hertz for this 300 hertz jet engine. Okay. What about the guy behind? Okay. Well, all you have to do is change this minus to a plus, because that would have the opposite effect. Okay. So the source would be going away from this guy. All I have to do is scroll up, scroll over, and replace the minus with the plus. That looks like 232 hertz. That's what this guy perceives. Something like that. Okay, so that. Oh, yeah.
How do you get whether it's positive or negative?
Yeah, so I've seen other explanations, like if things going to the right or to the left, there's a way to figure it out, but I like to go through this thought process of figuring out, should it be increasing or decreasing? Should it be greater than or less than the source frequency? So think about how fractions work, right? Like if I take the original, or here, we just focus on what's in parentheses, because if what's in parentheses is greater than 1, it's going to pump it up the frequency. If it's less than 1, it's going to decrease it, right? So if I do 340 over 340, it's speed of sound over speed of sound, that is 1. Okay? So what if I want to pump up the frequency? Because I know this guy hears more than 300 hertz. Well, I would have to have a small denominator to make that happen. Because, so for example, 340 over 340 minus 100, that's a ratio that's bigger than 1. It's like 1.42. Okay? Versus if I added on the bottom, that would make the denominator huge, which would make this overall fraction less than 1, makes it like 0.77, right? Right. Which would be like a lower frequency. Okay? So yeah, so I think it's that's how I like to do it. I like to navigate each particular situation like that. Right. Now there is an extra twist on top of all this, which is that these two observers, which I just had standing around, just looking at the plane, they could actually be running around themselves, and that would have an effect too, wouldn't it? So that's, I'm going to add even more to this formula. It's a plus or minus the velocity of the observer on the top here. Okay, so that's the full Doppler formula right there. Now, what if this? So one last little thing. What if, let's focus on this guy again. What if the jet plane is headed towards this guy, and this guy is also running towards the plane, so they're running towards each other? Right? Wouldn't each of those effects increase the observed frequency? Right? They would both increase. And so that would be minus on bottom for reasons we talked about. But what would go on top, plus or minus? Oh, plus, because that would further increase the observed frequency, right? So if they're running towards each other, be plus on top, minus on bottom. Okay. Guys get that? All right. I have one more thing I need to tell you guys about today, and that is decibels. So this is how you can measure how loud a sound is. Actually, decibels are good for measuring a lot of things that are logarithmic, but very commonly it's used to measure like sound loudness. So if you hear something like something is like 68 decibels, what does that really mean? And this is a logarithmic concept, a lot like it was for the Richter scale. Remember earlier today I was talking about earthquakes and saying that if you have, say, a magnitude 7 quake, you're really reading the exponent. It's really 10 to the power 7 is the intensity of the earthquake. And then magnitude 8 is really 10 times the intensity of the 7. And 9 is 10 times an 8. Decibels is the exact same idea. So why are we thinking logarithmically? Well, it's because you have like wildly varying intensities, but our brains perceive them as like not varying that wildly differently. Let me show you guys what I mean. So I got some groups of stars here. You guys see 9 different piles of stars, and I got 1 star, 2 stars, 3 stars, 4, 5, 6, 7, 8, and then this pile has 9 stars. Right, so all different numbers of stars. Okay. I got a question for you guys. Which one of those piles of stars contains the middle number of stars? Which one has the middle number of stars? And you guys say, you guys like 5? I'm hearing some of you guys say 5, but that's true. It is 5. Actually, there's 2 correct answers, and 5 is true from a linear counting perspective. So if you count like 1, 2, 3, 4, 5, you say, well, 5 is halfway between 1 and 9 in a linear sense. But tell you what though, counting 1, 2, 3, 4, 5, like thinking that way mathematically, that's something you actually had to be trained to do from a young age, from being a kid. And here's why, because our brains don't actually naturally think that way. There's all sorts of ways our brains actually perceive the world logarithmically. There's lots of examples to this. One of them is actually sound level. If you throw this exact same question to like a 2-year-old kid who's just barely learned to talk but hasn't really learned to count yet, most 2-year-old kids will all agree on the middle number of stars, and it's not 5. If it's not 5, what's the next best answer? 3. I'll show you guys why 3. Because if you start with the smallest number and multiply by a factor of 3, that gets you to 3. Multiply that by a factor of 3, that gets you to the biggest pile. So 3 is halfway in terms of like thinking logarithmically. Or how about this? If you take the biggest pile, 9, instead of multiplying by half to get to somewhere around this ballpark, what if you put it to the power of a half? You guys remember what power 1/2 is? That's the same thing as a what? Square root. Which is also 3, right? So square root is half logarithmically. Also, if you go to, let's say you find some tribe out in the middle of like Papua New Guinea, out in the jungles, who's not really a lot of contact with math or education, and you ask them, what's the middle number of stars? They will pretty universally agree it's also the one with 3 stars in it. So that's how our brains naturally perceive the world, including how our brains interpret sound level. So I'm going to give you guys a couple of formulas. There's actually a lot of formulas to go with decibels. I'll give you guys 2 of them, and then give you guys a table of examples. Right, so one way to measure decibels is sound pressure level. And another way is sound intensity level. Okay. You can measure both of these in some number of decibels. What's the formula for each one of these? So, right, formula first, I'll go back and explain it. Okay. So, sound pressure level, it's 20 times log base 10 of some number of pascals. Because you guys know sound is a pressure wave. Pressure, Pascal, is measured in pascals, right? Like newtons per square meter. Compared to, because decibels is really a comparison thing. You're comparing it to what? To some base value. Now this is going to seem kind of arbitrary, like people made it up, but it does come from somewhere you guys will see in a few minutes. 2 times 10 to the negative 5 pascals. Right? So it's sort of like the base value you're comparing to that. And the unit for this would be dB, like decibels. Okay? What about in terms of intensity? That was in terms of pressure. In terms of intensity, you can say it's 10 times log base 10 of some number of, now intensity is watts per square meter. You guys know watts measures power. So if you spread out some power over some area, right, watts per square meter, that's intensity. Compared to a base value of 10 to the negative 12 watts per square meter. To be that number of decibels also. Okay? Okay, go back and try to explain this a bit. Let's start with the intensity level one. So you see that this is a good way to take orders of magnitude and crunch it down to something that's maybe more linear, that our brains, like counting 1, 2, 3, are better at understanding. Right? A lot like the Richter scale with earthquakes. So we're counting how many orders of magnitude is something intensity above some base value. Right? And if you take the log of that, you're effectively getting the exponent, just like I showed you guys with the Richter scale with earthquake readings. Right? So log base 10 of something, you get some number of bells. That's sort of like the base unit for like how loud something would be bells. Now, I don't know why, but nobody ever reports anything in bells. They always say decibels. That's what you always hear is decibels. But you guys know what the prefix deci is. That's a tenth of something, right? So suppose you ran the numbers, just make up a number. Let's say this comes out to be 1 bell. 1 bell. How many decibels is equal to 1 bell? How many dimes in a dollar? 10, right? That's what this times 10 is all about, right? That it takes care of the deci. You guys see that? So this is some number of bells, just applying the logarithm, and 10 times it tells you how many decibels. You guys see that? Okay. What about the pressure level though? Why is it 20? All right, so gonna admit to you guys, I don't 100% understand this, but I'll do my best explanation. So 20 is actually 2 times 10. So it is still 10 to take care of this deci, but also times a factor of 2. Now where's the 2 come from? It has something to do with the fact that pressure is directly proportional to the square of power, right? The square of power. And you guys might remember this from a math class. If you take log of something squared, you can take that square and move it out in front as a multiple. That's why it's a factor of 2, because it's really pressure being squared to bring it up to the power level. Right? Okay, so there we go, so something like that. Let me give you guys a table of values so we can see some examples and see how the numbers play out, and why logarithms would be particularly helpful to describe something like this, like sound logarithms. Okay. Right, so we're going to pick some different sounds. We're going to look at what's the pressure related to that sound in pascals, like newton per square meter. We're going to look at what's the intensity of that sound in watts per square meter. And finally, how many dB is this? How many decibels, like the loudness? The 4 sounds we're going to look at threshold of hearing. That's to say, like the quietest sound that you can perceive. Like your ears can just pick it up and like, I think I hear a sound. We're going to do talking. So maybe like me talking to you right now. We'll do loud music. And finally, threshold of pain. Now, why pain? Well, we are talking about pressure waves, and your eardrums are made out of physical material. And if you play a sound too loud, then that pressure can physically tear your eardrums apart. Ouch, wonder how loud that is? We're about to find out. So, threshold of hearing is about 0.00002 pascals. You can call that like 2 times 10 to the negative 5 pascals. Okay? So very tiny number of newtons per square meter. Hey, that number, 2 times 10 to the minus 5. That's this number right here. Okay, I see sort of where this is coming from. Now, of course, this is just an equation people made up, but this is geared towards human hearing, isn't it? Okay? This is like the base value. The intensity that corresponds to is like 10 to the negative 12 watt per square meter. All right, let's run some calculations, see how many decibels that is. Okay, so that I'm getting. Do you guys see? I hope you guys caught on to this. That the first equation applies to this column, and the second equation applies to this column. You guys see that? Okay, so we'll run each one of these. 20 times log base 10 of some number divided by itself. You guys see that this number and this number is the same thing. So anything divided by itself is 1, right? So this is going to come out to 1. Okay. Does anybody remember what is log of 1? It's 0. Okay. So how many decibels would that be? Well, it'd be 0 decibels. Now that doesn't mean 0 sound. That just means you're at the base value. You can go negative decibels, but just like negative exponents don't make the number negative, they just make it smaller and smaller. Okay, so negative decibels would just mean quieter than the base value. Okay, so this is at the base value. What if I do it in terms of intensity though? I have 10 to the negative 12 watt per square meter. Oh, well look, that number is that number, isn't it? So it would be the same story. You play out the same way. 10 to the negative 12 compared to 10 to the negative 12 is 1. Log of 1 is 0. It's still 0 decibels. Okay, makes sense? Okay, next row, talking. This is about 0.02 pascals or 10 to the negative 6 watt per square meter. So let's try this out. What is 20 times log base 10 of 0.02 pascals compared to open parentheses 2 by 10 to the negative 5 pascals? That gives me 60 dB, 60 decibels. Right? Or in terms of intensity, that was in terms of pressure using this top formula. What about in terms of intensity using the second formula? That's 10 times log base 10 of, say, 10 to the negative 6 watt per square meter compared to 10 to the negative 12 watt per square meter. You guys see that's going to be 6 orders of magnitude. 10 to the negative 6 compared to 10 to the negative 12. That's like 6 orders of magnitude, right? Log base 10 of that tells you 6, and then times 10 gives you, oh, also 60 decibels, right? 6 times 10, right? 6 orders of magnitude. How about loud music? That would be about 0.2 pascals. Or the corresponding intensity is 10 to the negative 4 watt per square meter. In terms of pressure, that's a factor of 10. In terms of intensity, it's a factor of 100, right? Negative 6 to negative 4 power. But that's taken care of in this factor of 10 versus this factor of 20. So that's also corresponds to that. Right. How many decibels is this? Well, what is 20 times log base 10 of 0.2 pascals compared to 2 by 10 to the negative 5? We're looking at 80 dB, 80 decibels, versus if you apply the intensity level formula right here, we got 10 log base 10, 10 to the negative 4 compared to 10 to the negative 12. Well, it's still 80. Right? I mean, it's the same sound, right? So 80 decibels. I'm just showing you guys 2 different formulas, 2 different methods. They lead to the same number of decibels. Okay. And then threshold of pain. This is 20 pascals. Okay. So see the 4 examples, they're many orders of magnitude away from each other. Okay, so if you didn't see it before, but you see now why a logarithmic scale would be really appropriate for the situation, right? You've got many orders of magnitude different. Intensity is about 1 watt per square meter, right? Many orders of magnitude different. How many decibels does that correspond to? Well, it's 20 log base 10 of 20 divided by 2 by 10 to the negative 5. That's 120 decibels, or if I use the intensity equation, what is 10 log base 10 of 1 compared to 10 to the negative 12, that's also 120 decibels, because it's 12 orders of magnitude different, times 10 gives you 120, right? There you go, there's what decibels mean. So now, if you hear something like 68 decibels, you can have an idea of what that means. Your brain would perceive that as maybe like louder than talking, maybe like yelling or talking through a megaphone or something like that. I think that's what that would correspond to. But in terms of like something closer to base SI units, like in terms of pressure intensity, those would be like orders of magnitude different from each other. All right, oh, that's a perfect pause point. So tomorrow we'll do probably a couple of demos with you guys, I think I still have, and then I think plan is to start those book problems with you guys so you can start to get some of those.